All right, it's 1 o'clock. We can officially start. So we're not going to spend too much time going through problems in this direction. That is to say, starting with a molecule and trying to work out the details of NMR. We will spend more time going the other way. So if you are given a signal, what does it tell you about your molecule, its structure, and that specific environment? So it is worth going through this just to make sure we're all on the right page and specifically that we understand splitting. That being said, are there any questions about splitting in general? No. All right. So you're adding one because everything has a signal. You have no hydrogens on neighboring carbons, you have a singlet. If you have one neighbor, you have a doublet. So you keep adding one more peak to get up to however many number of hydrogens you have on neighboring carbons. So let's go through these. Oh, everything we did on Friday is still true for each signal. So the number of environments will tell you how many signals you have. And then within each signal, there's 3 pieces of information that you'll have simultaneously. It is absolutely worth labeling the units for each of those things because it's really easy to mess them up. So 3 ppm means something. 3 hydrogens for an integral means something else. 3 peaks in your signal means something completely different. So those will all be small numbers. 2 of the 3 will always be whole numbers, but it's really important that you write down your units and keep track of which is which. So what does integral tell you? Something integrates to 3H in that environment. So there are 3 hydrogens in that environment. What if it splits into a triplet? What does that tell you? 2 hydrogens on neighboring carbons, right? So that's about the neighbors. And then if it's at 3 ppm, what does that mean? So chemical shift, the ppm tells you about proximity to nearby functional groups, specifically if it's around 3.
Nitrogen.
Yep.
Halogen.
Yep.
And oxygen.
Right, so or oxygen. So probably one of those things next door. So all of those things are telling you different things. They're all simple, I think, taken one at a time, but you do have to consider them all together. So it's really easy to get confused. So try your hardest to keep them separate from each other. All right, and it all starts with drawing all of your hydrogens. You guys did great on the number of environments. The only ones that got messed up a little bit, don't forget that there is a hydrogen there. Don't forget that carbons make 4 bonds. So draw in all of your hydrogens where you can. This is a carbon right here, but it doesn't have any hydrogens. All right, so the next thing would be, here we'll put all of these together. Environment A, environment B, C, D, and E. Going through and doing chemical shifts, everything that is right next to a carbonyl would probably be in the 1 to 1.5 ppm region. Oh, sorry, 2 to 2.5. So those are both likely 2 to 2.5 ppm. These environments A and D are a little bit farther away from the carbonyl, so they may feel a slight tug to the left, but not very much. So if you shifted them up a little bit, that's fine. So maybe 1.25 to 1.75. I would expect the CH3s in environment A to be on the low end of that, and probably this environment D to be a little bit more on the high end of that, but that's okay, they're roughly in that region. E is too far away to feel much of anything. So 1 to 1.5, again, this is a CH3, so it's probably closer to the bottom end of that, so probably closer to 1. All right, so that's chemical shifts. The next thing is the relative integral. That is hopefully pretty straightforward. That's just the number of hydrogens in the environment. So this is 6H, 1H, 2H, 2H, and 3H. All right, so lastly, the new thing for today was the splitting. So when we're doing splitting, we are specifically looking at one environment at a time. And for these CH3s, it's easy to get confused on this because you have 6 different hydrogens in this environment. But think of them as they're all just basically living in the same house. So when they look out the window at their neighbors, how many neighbors do they have? Or how many hydrogens on neighboring carbons? So environment A, just 1, right? It doesn't matter that there's 6 of them all in the same environment in terms of splitting. What matters is they all have one neighbor. So So you don't have 6 neighbors, you just have the 1. So this environment A would split into a doublet, because even if there's 6 people looking out the window, they all only see the 1 neighbor. They only have that 1 neighbor. Does that make sense? All right, so from B's point of view, B has an integral of 1 because it is 1 hydrogen, but it has 6 hydrogens living on neighboring carbons. So you'll notice the way that I circled these environments, I included the carbons with them. We're not looking at carbons, but we're looking at CHs next to CHs for the neighbors. So if you lump together the CHs and then you lump together their neighboring CHs, you can see that they're kind of next door. If you draw out the bonds, it's a little bit deceptive because if you just think about it from this hydrogen's point of view, it might be easy to say, well, that's its neighboring carbon and that doesn't have any hydrogens. But instead, lump it all together. Think of it like this thing next to this thing. It's kind of the hydrogens living in a house next to the hydrogens living in this house next door. So we're looking at carbons next to carbons, even though we're counting the number of hydrogens attached to those carbons. So these are CH3s next to a CH. This is a CH next to a CH3. If you've got a neighbor, your neighbor has you as a neighbor. So going to this CH right here, it has 6 hydrogens in the carbon next door. So what would be the splitting? Just add 1. Yeah, just 7 peaks. So this would be 1H, but it's 7 peaks. It doesn't always work out that small integrals have large number of peaks and large integrals have small number of peaks. It's mostly coincidental. All right, so moving over here to environment C, this integrates to 2 because there's 2 hydrogens within that region. But looking at its neighbors, it's got a carbon on the left side, which has no hydrogens. It's got a carbon on the right side which has 2 hydrogens. So Bree, how many neighbors does it have? How many hydrogens on neighboring carbons for environment C? So 0 hydrogens on the left carbon, 2 hydrogens on the right carbon. 2. So you got 2 hydrogens on neighboring carbons. What would your splitting be? Just add 1. 3, yeah, so 3 peaks or a triplet. So this environment C would be a triplet. I'm never going to ask you to draw the actual spectrum, but this is what it would look like. It would have 3 peaks, 1 to 2 to 1. All right, let's go on down to environment D. All right, Kylie, so you're in environment D. You live on a carbon with 2 hydrogens. That just tells you your integral. But when you look out the window, how many hydrogens do you have on neighboring carbons? 5. Everybody got that? So from carbon D's point of view, you've got 2 on the left, 3 on the right, so 5 hydrogen neighbors. So what would your splitting look like? Right, 6 peaks. So environment D would have 6 peaks. 1, 2, 3, 4, 5, 6. Kind of be a big mess. It's not really a mess. They work out very nicely in terms of their splitting. All right, so then moving on to E, this is our last one. This CH3, it has D as its neighbor. So 2 hydrogens on its neighbor environment. Add 1 is 3. So this is also going to be a triplet. So peak E and peak C, or signal E and signal C, would both be triplets because they're both just next to the same CH2. They both only have 2 hydrogens on neighboring carbons, and that's what they've got. Any questions on any of that splitting? It gets really repetitive. You see the same kind of peaks over and over again. All right, a couple quick weird ones for you. All right, what if you are in this environment right here? What would your splitting be? Madeline, what do you think? So you are a CH2. Got a CH3 on one side and an OH on the other. Okay. No. I'd rather walk into traps together than to do it on a quiz. OHs and CHs don't usually split each other. So we're just looking for CHs and then hydrogens on neighboring carbons. So imagine when you've got an oxygen or a nitrogen in between, it's like a huge wall between neighbors. Yes, they're there, but you can't see them, you can't interact, you don't even know they're present. So this would only be split by the 3 on the left. Your OH would not split it. So one more shot. Yes, so this would just be a quartet, 4 peaks. This OH, I would expect to be a singlet. Sometimes an OH is a broad singlet, sometimes it's pretty sharp. If it's a broad singlet, it definitely means it's an OH or an NH. The reason why is that OHs and NHs are more acidic, so the hydrogen can actually fall off and go back on again. So you end up with sometimes, but not always, a broad peak. All right, so that is one weird one. Let me give you this one. So here is a benzene ring. All right, so be careful. Savannah, how many neighbors does this environment here have? This one right there. No, this is kind of a trick question. Just look at neighboring carbons. Okay, so it's got the carbons that are next, just next door neighbors. It does have 2 carbon neighbors, yes. This carbon and this carbon right there. So how many hydrogens are on its neighboring carbons? Just 3, exactly. So from this carbon's point of view, yes, it's next to a benzene ring. Yes, the benzene ring has 5 hydrogens, but a benzene ring is a larger structure. We really zoom in, and these carbons can only see what's on their next door neighbors, their neighboring carbons. So from this CH2's point of view, it has 3 hydrogens on the right side and 0 on the left side. 3 plus 0 is just 3. So it wouldn't actually split and see any of those hydrogens because none of them are on its neighboring carbons. So benzene is often tricky the first time you see it because you want to kind of lump all of those hydrogens in because they are on a neighboring functional group, but we're still just looking at neighboring carbons. So this would be a quartet because it just has these 3 hydrogens right here as neighbors. All right. All right, what about that CH3 right there? This is acetaldehyde. Kayla, what do you think? All right, so here's your environment. Here's your neighboring carbon. Does the neighboring carbon have any hydrogens attached? Yes. So what would the splitting be? Correct. So sometimes it looks a little bit weird when we draw out C-H instead of CH. So this is part of why I would recommend that you guys, when you're drawing them, just lump them together. There's the CH, there's the CH3. If you do it consistently, it becomes easier to see who's next door. It's again, kind of part of the problem with the benzene ring is we don't usually write this as a CH. We usually write it as a line. But think of these as lumped together. CH, 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 CH. And then that's a C with no H's. So just looking at your carbon with the hydrogen, that's one environment. Just move over and look at those carbons. So when we start to do this backwards, what we will see for each of these environments is what we have, and then you'll see information about the neighbors. They're not represented in the signal, but you know that they're there. You know that you're aware of their presence. And sometimes you can tell a little bit of information about functional groups farther away, but not about any more hydrogens. All right, so let's move down and do this backwards because doing this backwards is the meaningful skill and the one that you'll be quizzed on. So you will have 2 different types of questions on your quiz on Wednesday, and they're all about decoding signals. So we're looking at these signals one at a time. I will ask you, here's information about a signal. What general information does that give us? Or I'll give you a signal and say which of these molecules could fit. And we'll practice both of those things today. All right, so you guys did these already. They went pretty well, but we'll go through them together and then we'll start on some fresh ones. we've got 3 pieces of information. Yeah. And we kind of need to integrate all of them. We've got the splitting, the integral, and the chemical shift. I would recommend that you always start with your integral because the integral tells you about what you are. The chemical shift tells you what you're near for the most part. And the splitting tells you hydrogens on neighboring carbons. So once again, what you're near. So this is what you are, and these 2 things are what you near. The only time that I would recommend going in a different direction to start off with is if your chemical shift is above 5. So let's say your chemical shift is 10 to 12. What does that tell you? 10 to 12 ppm. Yeah, carboxylic acid. And so at that point, you're not really looking for what you're near. It's just kind of that's what defines what you are. But being in these regions like 2 to 3, these are probably just alkanes or CHs that are near stuff as opposed to being part of stuff. All right, so if we start with this, 1H means that you are a CH. And I would write it out and I would circle it because that's what we're looking at. That's the environment that we are indicating with this signal. Everything else is just about proximity. What does 2.6 ppm tell you? It's kind of close to 2 to 2.5. So what could be next door? Yep, a C double bond C or a C double bond O. Yeah, a C double bond O, a C triple bond N, a C triple bond C, a benzene ring. Do you know which one? You don't. This is all the information you've got. So I would recommend you don't back yourself into a corner and say, it's definitely a carbonyl. Because then you're just guessing. And maybe you're right, or maybe you're wrong. But if you're more general and you say, I'm next to some carbon-containing functional group, good. You're general, you're broad, and you must be correct. So I would write just carbon-containing functional group. If you wanted to, write carbonyl / alkene / alkyne / nitrile / benzene ring. But don't back yourself into a corner and say it's got to be this, because you don't know that. When you start to put these together to make a molecule, if you're just wildly guessing and you're wildly guessing wrong, you're tricking yourself. So stick with what you know and go with that. All right. What about a 7-peak signal? What does splitting of 7 tell you?
6 neighbors of hydrogen.
Yeah, 6 hydrogens on neighboring carbons. So we only really have 2 more spots. So what must they be? Yeah, so they're probably both CH3s. All right, little asterisk. It's possible that your carbon-containing functional group has a hydrogen on the first carbon, which would mean that you would only need 5 more, but this is much more likely that that's your answer. All right, questions on that one? All right, moving on down. Once again, we're integrating to 1H. So we are a CH most likely. You can do the rest of this in whatever order you see fit. But if we're at 3.8 ppm, we're definitely in that 3 to 4 region. So what does that tell me? Yeah, ON or X directly next door. You don't know which, so don't commit. Just go O/N/X. Don't forget X means a halogen in general. So it's chlorine or bromine or iodine or whatever you don't know. And remember, in organic chemistry, we don't have that many elements that we use. We use hydrogen, carbon, nitrogen, oxygen, and halogen. So this is pretty broad because this is really of those 5 things. It just means there's one of the 3 most electronegative ones. And then we've got a splitting of 5. What does a splitting of 5 tell you? Right, so if you got 4 hydrogens on neighboring carbons, what could it be? How could they be distributed? Yeah, so it could be 2 CH2s. Or how else could this exist? How else could you get 4 neighbors? Right, a CH3 and a CH. Would you know, based on this signal, which one of those situations is yours? You wouldn't, because they would both look the same. The only way you would be able to figure this out is to look at the rest of the NMR. You guys are not looking at whole NMRs and trying to figure everything else out. We will start doing that later on this week and into next week, but for now we're just doing one signal at a time. Real quick sneak preview, kind of the way you would figure out whether it was this one or that one is to look at the other peaks. If the other peaks in your spectra had a bunch of CH2s, it's probably this one. If you didn't have any CH2s, it's probably that one. So you get to use kind of more context clues of the other signals to help put this stuff together. Last one, this is the simplest one probably. It's 3H, so it is a CH3. It's a singlet, meaning that it has no hydrogens on neighboring carbons. Then it's at 3.2 ppm. So once again, it's just next to O or N or X. And at that point, we would not be able to tell. That would be the end of our situation. Okay, questions about any of those? All right. Great, I am going to switch to a whiteboard and just start calling on you, and we will just work through as many examples of this today as we can. And that's our goal. My goal is to call on all of you at least twice for the next 40 minutes. All right, 6 peaks. So I'm going to just give you information. I hope you can see that. 6 peaks, 2 hydrogens, the integral, 1.32 ppm. What this would look like on an NMR would be, you would have this signal. That's 6 peaks. Oh, that was a 7th. 1, 2, 3, 4, 5, 6. And it would integrate to 2H, which the instrument would just add up those pixels. And then you would find this somewhere between like 1 and 2 ppm on the chemical shift scale. So this is just the written out information for what you would read by looking at that signal. But what does that tell us about the environment? Bree, you get to go first. We're just gonna kind of go clockwise. Are you ready? Okay, so what should we do first? What do you think? Great. So you are a CH2, and I would really highly recommend you circle that. Just got to keep everything straight. Right? Yep. And so your chemical shift is 1.32 ppm. Does that give you any more information about this molecule? Not really. I mean, you can kind of, by process of elimination, say that that makes sense for an alkane. So there's probably not like an O or an N or an X there, but this is perfectly fine as an answer for me. You're a CH2, you got a CH2 on one side and a CH3 on the other. Questions on that one? All right, good. All right. Caleb, you've got a singlet. It integrates to 3H. It's at 2.24 ppm. What does that tell you?
So you start with CH3.
Okay.
And you have no hydrogen there.
Correct.
It's bonded. Double bond up.
So it could be a C double bond O. What else could it be? There's quite a few possibilities. What do they all have in common?
Oh, so it's like a double bond hydrogen out.
So it's not an O or an N or an X, because those would all bring you up to 3 to 4. So kind of everything else is just all those carbon containing functional groups. And so I would just say you're next to one of those and you wouldn't know which one. So you can summarize it in a lot of different ways. My shortest abbreviation for all of that is just CCFG, carbon containing functional group. But that's pretty meaningless if you don't know what CCFG is. So if you want to, you can do it this way. C double bond C slash C triple bond C slash benzene slash C double bond O slash C triple bond N. but it's got to be next to one of those things. So alternatively, I find that easier, but just know that you're next to some functional group, but not an oxygen or nitrogen or halogen. And that's it. Right, questions on that one? All right. Bum, 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 bum. Madeline Hardy, you integrate to 1H and you are a triplet and you are at 5.41 ppm.
So it's gonna be 5CH.
Yes.
And it's gonna be double bonded to a C.
Yes, good. All right, let's pause there for a second. So anytime your chemical shift is like higher than 5, it's part of a functional group, meaning it is on a functional group as opposed to being next to or near a functional group. So 5.41 tells us that, like you said, you have a CH, it's part of a C double bond C. I know for those of you in the class, I'm going to be repeating most of what you say. It's so that those in Zoom can hear you as well. But good, this is what you've got. So how does the triplet help us?
It needs 2 carbon neighbors. No, 2 hydrogen.
Yep, 2 hydrogens on neighboring carbons. All right, no judgment. Did you watch all the way to the end of the video and pay attention to complex splitting?
No.
Okay, anybody do all of that stuff? Yes, maybe, no? All right, here's the deal with complex splitting. It only happens in alkenes. It is incredibly rare, and it is also not very helpful compared to everything else. So while it was about half of that video, it was less helpful than the first half, more complicated than the first half, and more rare than the first half, which is why I wanted you guys to pay a lot more attention to the first half. If you didn't do the second half, it's totally okay. All right, here's how it works with alkenes in really quick general. Hydrogens that are cis to each other or trans to each other split differently than neighbors normally do. So if you had 2 H's here, it wouldn't really give you a triplet. It would split out as something significantly more complicated. So in order to have a triplet, you absolutely just need to be next to a CH2. So how could this CH just have a CH2 next door? Yep. So this is where you are, and this would have to be what you're next to. So if these words matter to you, great. If they don't, it's okay. I'm not going to give you any doublets of triplets or anything like that on your quiz on Wednesday. All right. So that's as close as we're going to get to complex splitting. Sound good? All right. You do need to know what 5.4 ppm means, though. Okay, moving on. All right, Savannah, you have a singlet. It integrates to 5H, and it is around 7.21 ppm. So this right here is probably the most important and helpful part. Yep, you got a benzene ring, right. So drawing out a benzene ring, if you got a benzene ring and you integrate to 5, what does the integral tell you? What does this 5H mean? Mm-hmm. Mm-hmm. So how many hydrogens are on your benzene ring? Great, that's it. So there are 6 spots on a benzene ring. And you just know that 5 of them are hydrogens. All right, benzene ring splitting is quite variable. Sometimes they all just end up mostly on top of each other, and it might look like this. which kind of looked like a singlet. And sometimes it'll just be like a huge mess of stuff. So sometimes we'll use the term multiplet for this, multiplet being a very general, indecipherable signal. Don't use that any other time, please. But it just kind of, sometimes these are a mess and sometimes they're simple. It's because of complex splitting. You get complex splitting sometimes in a benzene ring and sometimes you don't. But the splitting doesn't really matter because what you said, it's on a benzene ring and it's 5 hydrogens. That's all you need to know.
So if it wasn't a singlet, like, let's say it was like a triplet or something, it would just be CH2 on the extra, or will it ever be that?
Nope, it would have to be hydrogens directly attached to the benzene ring. And so really the splitting that you see doesn't matter whatsoever. It is 5 hydrogens on the benzene ring, and that's all you need to know. Because there's no other way to draw a benzene ring with 5 hydrogens. I mean, you could steer it around and have the blank spot be at the top or the left, but it's all spinnable. So much like complex splitting is complicated, but not actually usually for you guys too important. There's going to be times when it's super important, but they're relatively rare. For a benzene ring, like it's 5 hydrogens on a benzene ring. There's only one way to draw that. Splitting doesn't tell you anything you don't know already. So it's complicated, but since it doesn't matter, good news. You don't have to worry about it. So this is part of why I would look at this chemical shift first. Again, if it's 5 or above, which it is here as well, then start there because that gives you a lot more information. You won't be slugging through to figure out other things. All right, that was a weird one. Good job. All right, Sydney, you ready? Doublet, 3 hydrogens, 1.82 ppm.
So it's a CH3
Okay,
and has 1 hydrogen neighbor,
okay. How could it have 1 hydrogen neighbor?
the doublet,
Right, but what's next to it?
oh, carbon,
Yep, so CH next door.
and 1.82 is between, it's a little higher than the regular, so I guess it's got a C next to the CCF thing that you said, CCF2.
Maybe? This is really, you don't know a lot about this. So CH3 is definitely true, right? Everybody go with that? And it's definitely next to a CH. 1.82 is kind of in the middle of nowhere. It's not really a range that we have. So this CH3 is not next to a carbon containing function group, and it's not next to an O, N, or X, but it is higher than an alkane should be. So it's probably 2 doors down from something. So 2 doors down from an O or an N or an X would shift it up by about a half, which seems about reasonable. Being 2 doors down from a carbon containing functional group shifts you up by a little bit. And this is arguably a little bit higher than it should be. So that also seems reasonable. It could also be next to it's 2 doors down from 2 carbon containing functional groups. I don't really know. But it's definitely 2 doors down from something. Does that sound fair? You would not know by this thing alone what that something is, but I want you to be aware that it's 2 doors down from some functional group. And you can write that out however you want to. So, yep, something. Because let's flash back to this one for a second. In this case, it's not 2 doors down from anything. So this one, the top left, is the answer to the question, and there is no more to it. But in this case, that's not right with nothing there, because we would expect this CH3, if it was just part of an alkane, to show up right around 1 ppm. And 1.8 ppm is way higher than 1. So it's got to be 2 doors down from something. So if you were to write O/N/X, great. If you were to write carbon containing functional group over there, great. If you were to write really any functional group or anything like that, that's fine. Because you don't know for sure, but it's got to be 2 doors down from something. Otherwise, it would show up around 1. Does that sound fair? So that was a tricky one too.
I can't remember, when is it plus 0.25 versus plus 0.5?
So O or N or X is +2 if it's your neighbor and +0.5 if it's 2 doors down. The carbon containing functional groups are +1 if it's your neighbor and like 0.25 if you're 2 doors down. So more likely this is an O or an N or an X. That would probably be right. But in this case, I would make the case that you wouldn't be exactly sure. So it'd be okay to leave it other way. All right, Olivia, are you ready?
Yes.
All right, these are in some order, so they may be getting harder or easier, but it's just what I've got. All right. Singlet, 3H, 3.38 ppm.
It is a CH3. You said a singlet,
I did,
so no hydrogen neighbors.
right?
And either a N, O, or halogen.
Great. You know anything else?
Don't believe so.
You do not, and that's it. Questions on that one? All right, new sheet. We're going to go with a broad singlet. 1H, 10.58 ppm. All right, Kylie. Oop. So where do you want to start?
Was the broad, I remember that in the anatomy, was the broad one? Oh, I don't know.
So it's telling you that it's a hydrogen that's exchangeable, meaning that it's not a CH. But if you know what 10.58 is, then that becomes clear. Yes, what do we call that functional group? Carboxylic acid. So this is the hydrogen that is the hydrogen of a carboxylic acid. So it's not near a carboxylic acid or next to a carboxylic acid. It is the hydrogen that is part of the carboxylic acid. Acids are acidic, meaning that the hydrogen falls off pretty readily. So normally these will be quite broad. Alcohols are sometimes broad, sometimes not. Carboxylic acids are almost always broad. But you wouldn't know anything else about this, just that it's a carboxylic acid. So in this case, because if you know what 10 to 12 is, none of the rest of that information makes any difference to you. So it's a singlet, but an OH never splits with its neighbor. So you would have no idea of what else is attached to this. So that's it. Yep, you would have no idea. Yes, ma'am.
So the like 2 to 2.5, it's like a carbon and then attached to a carbon with something else. And then once it's over 5, it's directly attached to that carbon.
Yes, or that functional group, whatever it is.
Okay.
Yes, so just to recap those, so this one right here, like this is a CH that's next to a carbonyl, so this would be 2.5. This is an H that's part of the carboxylic acid. So that's where your 10 to 12 would be. So the H that's like, this one is 10 to 12. This is an aldehyde. So this hydrogen is part of or attached to the carbonyl in an aldehyde. So that one is 9 to 10, which would be different from, this is a double bond, oh, it's getting sloppy, sorry about that. That would be different from this CH down here. A CH next to the carbonyl would be that 2 to 2.5. Same thing here. If you got a CH next to that carbonyl, this one would be 2 to 2.5. If we've got a hydrogen that is attached to an alkene, so like this one right here, that would be 5 to 6. But you had a CH that's next to the alkene, where would that be? Give me the other way. So CH next to an alkene would be where? It's the same place as CH next to carbonyl.
2 to 2.5.
2 to 2.5. And then the same thing would be true for if you're looking at a benzene ring. The hydrogens that are directly attached to the benzene ring or part of the benzene ring, where do these guys show up? Yeah, 7 to 8. And what about a CH that's next to a benzene ring? Yeah, 2 to 2. So when you've got a benzene ring, you'll likely have both of those things. You'll have hydrogens directly attached to it that are 7 to 8. Then you'll probably, not necessarily always, but if you have a CH next to the benzene ring, it's 2 to 2.5. All right, Bree, you're back up again. I'm gonna give you the worst one. It's just number 8 on the list. Oh, nope, we're gonna get to that one later, sorry. This is not the worst one, it's just the next one. 8P, 1H, 1.36 ppm. Yep. Okay. Yes, you could do CH3, CH3, CH, and that is definitely possible. Or what else could it be? Correct. Once again, you would not know just by looking at that which one of these two situations it is. For the sake of the quiz on Wednesday, just pick one of the two and draw it. You don't have to draw all of them. But it's got to be one of those two things. 1.36 ppm, what is that telling us? Anything? Yeah, so it's probably not close to anything, anything electron withdrawing because it's just in that alkane region. All right, good. Caleb, you have a quartet. It integrates to 2H. It is at 2.52 ppm.
You're gonna start with CH2.
Great, I will start with the CH2. Sounds good. So what is it next to?
So it's next to a CH3 and a CCH.
Great. So the 2.52 tells you that you have some carbonyl or carbon containing functional group, maybe a carbonyl, maybe an alkene, maybe an alkyne, maybe a benzene ring, et cetera, et cetera, et cetera. But that's what we know. All right, good job. All right, new page. Let's do one more. All right, Madeline, you get the worst one, and then we're moving on to something else. All right, you have a 1H singlet at 2.05 ppm.
It's just going to be CH is 1H.
Okay.
And the 1P is not going to have any hydrogen neighbors.
Okay. Remember that. That's a super important part of this.
Okay. No hydrogen neighbors.
Okay.
It's going to be next to a carbon containing functional group.
Okay. Is everybody good with this so far? So this seems like what you know, right? Okay. What could possibly be right here, though?
It would have to be a C with all C's.
Exactly. Perfect. So because this is at 2.05, it's next to a carbon containing functional group, but it can't be next to an O or an N or an X. Otherwise, the chemical shift would be higher. it can't have a hydrogen right here because then it wouldn't integrate to 1, it would integrate to 2. So it must, by process of elimination, have a carbon there. But as you were so keen to point out, that carbon can't have any hydrogens either, because then you wouldn't be a singlet. So that must be a carbon with all carbons. What about right here? It would also have to be a carbon with all carbons. Does this look likely? It's theoretically possible, but it's a super weird situation. However, a 1H singlet is pretty common. A 1H singlet is probably not this. A 1H singlet is probably this. Or this. So when you see a 1H singlet, you will be able to probably figure out a situation in which you can make that work. But it's probably not going to line up with the rest of your molecule, because this is a really rare, weird fringe case. Much, much, much more likely, it's just an OH or it's just an NH.
So if you see that like on the foot, it needs to be OH.
I mean, if you draw this, it's not wrong for sure. But when next week, what we're going to start doing is taking these pieces and putting them together. And when you do that, this is going to be like a rabbit hole that you go down and you're never going to come out of. It's probably just one of these two things. And so this is where I want your mind to go first. A 1H singlet is most likely an OH or an NH. And the chemical shifts don't help you with NHs or OHs very much because they just show up kind of anywhere. So 1H singlet, I want you to think OH or NH, because that's most likely what it is.
How does it like complete the object for the carbon middle?
How does it complete what?
Like, are you saying that it's just like C to an H and then to an O? So like, then it would only be 2 bonds to carbon. Sorry, I haven't drawn out.
For this carbon containing functional group?
Oh, so you would keep the C, all the C's over there?
Yes, so this CCFG, these are not, this is just my initials for carbon containing functional group, meaning C double bond O / C double bond C / C triple bond C / C triple bond N / benzene. So,
But the like C's to the left and below, all that.
oh, yeah, so then these at that point could have hydrogens if they wanted to, because
But you're saying that's right.
I'm saying that this is pretty crazy and possible, but not very likely.
So why wouldn't it be like didn't you say C triple bond N is one of the carbon? So like.
Right.
Why wouldn't it just be C triple bond N and then that makes it no hydrogen move
Well, you mean on the right side or on all of the sides?
on the right side?
Okay, so this is
Okay,
possible,
okay, I see what you're saying.
but
I
then
wasn't
you'd
paying
yeah.
attention to the carbon.
It's not actually about this that messes it up. It's these crazy like terbutyl groups are the only way you would have no hydrogen neighbors. All right, does that make sense? So like you can, and you did, congratulations, figure out a way to have this work for a CH, but it's pretty unlikely that these things, 1H singlet, represent a CH. All right, so we are in the next 15 minutes, I'm gonna give you some structures and we are going to do some basically multiple choice matching questions. So go ahead and write these down. I'm gonna give you 6 structures. A, it's a pretty likely situation is that you're not starting from scratch. Much like lab last Monday, Tuesday, today, tomorrow. You're not randomly looking at a molecule. Usually you have some idea of what it could possibly be because you're the one that started the reaction or something like that. So when you run an NMR, a lot of times you're looking for not just trying to figure it out from scratch, but you're trying to match to a list of possibilities. So this is another quiz type question that you will probably see. And so that's what we're gonna do right now. So I don't remember where we left. Madeline went last. So Savannah, you get the first one here. Let's say that I run an NMR of my sample. I know that it's one of these 6 things. And I get a broad 1H singlet at 2.81 ppm. Which one of those 6 molecules could have a broad 1H singlet at 2.81 ppm?
So if it's 2.81, then that means that it's probably the size of carbon containing functional group or a egg.
All right, hold up. Back up just one second. So you're on the right track. What I would recommend you do is instead of trying to take this piece of information and figure out immediately which one matches, do what we did for the rest of today. Take this information and tell me what it could possibly mean. So based on what we just did a second ago, if you see a 1H singlet, specifically that it's broad, what is it more likely than not? OH or correct. That should make this problem much easier.
So it has to be.
Correct. So I highly recommend that what you guys do is take this information, turn it into the little picture that we've been doing up to this point, and then try to match that little picture to these things. So you do 2 little steps instead of 1 big step. All right, Olivia, you have a 1H singlet at 5.86 ppm.
So we know it's not an OH or an NH.
Right, so let's go with this is our operative information here, 5.86 ppm.
A C double bond to the C. So
How many hydrogens?
1
Okay, and is it next to the C double bond C or directly attached to the C in the alkene?
directly.
Perfect. So this is what we're looking for.
So it's
Well, good news, bad news. The bad news is there's multiple alkene containing molecules here.
C.
Okay, why do you say it's C?
Because I just saw the 1 hydrogen.
Okay, so all of these would be different environments. So that's a 1H, and this is a 1H, and that's 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 a 1H. So they all satisfy this,
Mhm.
and they all satisfy this. But what does a singlet mean?
It has no hydrogen neighbors.
Yeah, on neighboring carbons. So which one of those 8 hydrogens that I've drawn in blue on there, on alkenes, has no hydrogen neighbors? Correct. So this one right here, it's got that as a carbon neighbor and that as a carbon neighbor, and neither of those have any hydrogens. So this one would be a singlet. So C would be the correct answer. So you were right the first time, but let's make sure we know why. Okay, so this one would be a doublet. This one would be a doublet of doublets. This would be a doublet of doublets. This would be a doublet of quartets. That would be a doublet. That would be a doublet of doublets. That would be a doublet. That would be a singlet. All right. 3H triplet at 0.952 ppm. Sydney, ready?
I think so.
Okay.
So CH3
Okay.
and on the lower side, so it's probably not next to any.
Well, it is a triplet. What does that mean?
Oh, there's two hydrogen neighbors,
Okay, so what's it next to?
a CH and a CH, or just a CH2. Oh no, it's just a CH2 because it's three.
Exactly. Only one bond, so just the CH2. And then as you were saying before, it's on the low end of that, so it's not really near anything exciting. So which of one of those structures could match this?
Is it A on the farthest end?
All right, so A does have a CH3 right here. I know you guys probably can't see this because of this recording thing. I can't move that, unfortunately. But that's next to an alkene. And this one is at 0.9, so it's definitely not next to an alkene. All right, so those CH3s on A are both next to carbon-containing functional groups, so that wouldn't work.
Is it E?
Yep, so it's got to be E. That's the only one that has a CH3 next to a CH2. So it's part of this tail right here. It's the only one that has something like that. Good, good. All right. You ready for the last question? Okay. Seem to like to save the worst ones for last. So good luck. So 3H doublet at 1.89 ppm. So what can you tell me for sure? Great. Yeah, take your time. Right, one hydrogen on a neighboring carbon. Okay, so those things are for certain, correct? All right. So these things must be true. Chemical shift, as we have seen, sometimes goes a little bit outside of our expected region. So Sydney, we would expect that CH3 to be between 1 and 1.5, but it was at 0.95, and it was close, right? All right, in this case, you're at 1.9, and 1.9 is weird. 1.9 could mean a couple different things. It could mean, what do you think? What would be your expectation? Yeah, could we 2 doors down from something? So just trying to match up what we've got. Where do we have CH3s next to CHs? Because this we know for sure. So this one doesn't have any CH3s, so that's right out. This one has a CH3 right there, but its neighboring carbon doesn't have any hydrogens, right? So this could give you a CH3 singlet, but not a CH3 doublet, so that one's right out. This was a CH3 that's a triplet. We just did that one, so this one's right out. That doesn't have any CH3s, and that doesn't have any CH3s. So it has to be A, but let's look at this real quick. So this was a CH3. What it's next to is actually a carbon-containing functional group. And I like that this is actually where that peak shows up in this molecule. So this is a CH3 next to a CH, but this is a little bit lower than we would expect. We would expect this CH3 to be 2 to 2.5, but it's actually like 1.9, which is pretty close to 2, but it is a little lower than we would expect. And so this is part of, I guess, as we move forward into the next week, I want to impress on you that while you need to be able to make a reasonable guess for the integral and the splitting and the chemical shift, that the integral will be correct and right on. The splitting will be correct and right on. Chemical shift is a little bit flexible, kind of like with IR, where it could be a little higher or lower than you expect. We're looking at like maybe by 0.1 or maybe 0.2 outside of our expected region, but it is possible that it'll be a little higher or lower than we've laid out for those ranges. So if you're gonna get married to integral and chemical shift, or sorry, integral and splitting, and be a little bit flexible with your ppm, knowing that it's not outright lying to you, but sometimes it's a little bit outside of your expected returns. All right. Any questions on this? You can do this, right? So practice this stuff. There's a bunch of homework problems for today. And we will have a quiz on Wednesday, and then we'll start putting all these things together in Spectrum. Thanks. I'll see you in lab today or tomorrow or next Monday for class.